You said you use a small example, right? So first, what's the first one that we should check?
2. Or sorry, not 2, 3.
Okay, and 3 works or not?
Well, you can write it. That's what I'm trying to figure out. You can write it 1, 2, 3, 4, 5, 6, 7, 8, 9.
If you think it doesn't work, you should tell me a counter example. If you think it works, you should prove it.
Well, when you say works, you just mean like there's like any value. Yeah. I don't know how to prove that it really works or it doesn't work. The part you don't understand is how to approach proving that like all the possible arrangements are
So,
row arrangements can be transformed.
do you want a hint for solving and for proving N3?
Yeah.
Okay, so look, common difference can be what? If you consider, for example, the first row. What are possible values for the common difference?
1
1 or
and 3
2 or
1, 1, 1, 2,
is
and
3
3, right?
possible? 1, 4,
Yeah,
7.
1 for 7.
Is 4 possible?
No.
1,
Wait, is
5,
it 1,
9
5?
is
No.
possible, right?
You're saying just for the first row?
Yes,
Okay.
for example, one
Yeah.
of the rows, okay, not for all.
Okay.
But 5 is not possible, right? Common difference cannot be
Yeah.
5. Okay, so
Yeah.
here we want to check. We say, okay. For example, if we consider 1 without loss of generality, we can assume 1 is here, right?
Mm-hmm.
Okay, so let's consider different cases. We have 4 possible ways for the first row, right? And look, the permutation is not important that I write, for example, 1, 2, 3 or 1, 3, 2, because we can permute elements in each row, right?
Mm-hmm.
So the first row can be 1, 2, 3 or what?
1, 2, 3, or 1, 3, 5, or
Or
1, 4, 7, or 1, 5, 9.
exactly. Okay. Now for the second row. Do you agree 4 is in one of them without loss of generality? 4 is here.
Yeah.
Okay. Here also we can say 2 is here without loss of generality. 2 is here, 2 is here, right?
Mm-hmm.
Okay. For this one, common difference can be what?
Common difference can be 4. No, it can be 1.
No, for this row. Can be 1
Yeah.
or
1, 2, 4. That's it, right? 1 and 2.
that's it. Because 3 is not possible. 4, 7, 10, right?
Mm-hmm.
Okay, so here we can say, okay, 4, 5, 6 or 4, 6, 8, right?
Mm-hmm.
Then in this case, it will be 5, 7, 9, right?
Yeah.
Okay, so here, is it okay? Do you agree if we use 1, 1 and 4, the next one should be what? 7, right?
7. Yeah.
So 1, 4, 7, let's consider them like this. And then what? 2,
Then you have to do
6,
isn't
4, it's not possible.
that doesn't
2,
work.
8, and 5. 2, 8, 5 is good, right?
Would it have to be 2, 5, 8?
It is not important. It says you can permute.
Oh.
You can permute the rows, and look, it says in each row can be permuted to form an arithmetic progression. It shouldn't be in order, okay?
Mm-hmm.
Elements 3, 6, 9 also a common difference. So this table is good, right?
Mm-hmm.
7, 8, 9. Again, this table obviously is good. 3, 3, 3 common difference, right?
Yeah.
Okay, so what about 1, 3, 5 here for 2? What are the cases? What are the possible common difference for 2?
2 would be 2. So common difference 1, common difference 2.
Common difference 1 is not possible because then we have
Oh,
2,
that's
3,
true.
4. We've used 3 here, right?
And common difference 2, and that's it.
Yes, common difference 3 is not possible. 5 common difference 4 is not possible. So common difference can only be 2, which is 2, 4, 6, right? So 1, 2,
Yeah.
3, 4, 5, 6, 7, 8, 9. Again, we can say 1, 4, 7. And 3, 6, 9, right? 3, 6, 9, and the rest is same, right? 5, 2,
Mm-hmm.
8. Okay. So this table is also good. What about this one? Common difference of 2 is what?
Can be common difference 1 or 3.
Common 1 is not possible because then 2, 3, 4, right?
I didn't. Wait. Oh, yeah.
Okay, so common difference can be what numbers?
So 3.
Is 3 is 5, 8, only 3, right?
Mm-hmm.
1, 2, 3 here, 4, 5, 6, 7, 8, 9. Okay, so again you can say
Mm-hmm.
like this 1, 4, 7. Oh, no. Cannot use this. 1, 2, 3, 4, 5, 6. Oh, 7, 8, 9. Columns are good, right?
Mm-hmm.
What about this one?
2, 3, 4. That's good. Common
2.
difference
Common
1.
difference can be 1. Common difference can
Yeah.
be 2, right?
Yeah.
Common difference cannot be 3, cannot be 4. So common difference is 1 or, so let's try. If it is 1, 2, 3, 4. If it is 2, 4, 6. If it is 3, 5 is bad. If it is 4, it's bad. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, in this
Mm-hmm.
case, it's 1, 4, 7. And then what? 2, 8, 5. So 2, 8, 5 and 3, 6, 9. This is good. This one again, 1, 4, 7, 3, 6, 9, right? And
Yeah.
2, 5, 8. So 3 works, right?
Yeah.
Okay, I remember I saw this before, and I remember when we check a small example, we can prove. I think I proved for prime numbers it works, and for other numbers it doesn't work. Okay,
Mm-hmm.
so probably for n4 we can find counterexample, but we can try to let's generalize 3. 3 is a prime, right?
Mm-hmm.
And can you tell me if you consider 1, 2 to p squared? If we consider the remainders mod p, what are the remainders? How many remainders do we have from what number?
From, from 1 to p squared, then you have
How many
this
zeros are
thing.
there mod p?
Uh, 1p, 2p, 3p. So p.
Yes, how many ones are there?
Uh, also p.
Yes, because you can say 1, 2 to p, it is 1 box. P plus 1 to 2p, 1 box. The last
Mm-hmm.
box is p squared, right? So p
Mm-hmm.
from each of them, right?
Mm-hmm.
Okay, good. Now you should use this to prove p works. Want to try the rest on your own, or do you need another hint?
I can try.
Okay, sure.
Okay, so I'm not sure how to fully explain it, but so if you put, yeah, I still don't really get it or get how to prove it.
So, want me to explain?
Yeah.
Okay, sure. So, can you tell me if you consider only all cells mod P, in each row we can have what or what?
In each row we can have what we want. We can have common difference P.
No, the numbers that we have mod P are what?
0 to P minus 1.
Yes, one way is to 0, no, 1 0, 1 1, 1 2, 2 1 P minus 1. Exactly all these numbers. Okay? We have this, or all remainders are same. We have only these two cases. All remainders should be same, or all remainders should be different. Why? What's the reason here?
Well, if they all have the same, what's it called, mod P, then their common difference is just P. And otherwise,
So, if common difference has what property, then we can say we have these numbers.
it's to be 1 or. So I guess it's a divisor of P or N.
If D is a divisor, if P is a divisor of D, then we have this. Otherwise, we have. Sorry, we should. If P is not divisor, if P divides this, we have this. Otherwise, we have this, right? And do you know the proof is what, or want me to explain?
I don't know the proof.
Okay, so here, look, if P divides D, this one is obvious, right? Because A plus D will be multiple of P. Do you agree this one is easy? Because D is multiple of P, so D is what mod P?
D is 0 mod P.
D is 0 mod P, so do you agree then? Because it is 0 mod P, if the first one is A plus 0 is A, all of them are A, right?
Yeah.
Okay, now if P otherwise means P doesn't divide D. Prove that if P doesn't divide D, we see all the remainders. You want to try it on your own, or do you want a hint?
So if P doesn't divide D, it has to be all remainders.
Yes, we will see all remainders exactly, each remainder exactly once in the row. Want to try it on your own, or do you need a hint?
Yeah, I'll try it.
Okay, sure.
Can you explain it?
Okay, sure. So here we know common difference is D, and D is not multiple of P, right? So it starts, for example, from B, then B plus D, B plus 2D, and the last one is what?
B plus B plus PD. Or P minus
P minus 1 times D, right? Agreed?
Yeah.
Okay. Do you agree if we prove that these numbers are different mod P because they are P numbers, then one of them is 0, one of them 1, one of them 2, to one of them P minus 1, right?
Yeah.
So suppose that two of them are congruent mod B. B plus ID is congruent to B plus J mod B. Then what can we say?
I is congruent to J mod P.
Yes, you can say ID is congruent to JD first, then you can divide both sides by B. And because P doesn't divide B, GCD of D and P is 1, so I is congruent to J mod P. So, and we know I and J are from what to what?
I and J are from what to what? I and J are from 0 or from 1 to
0 to, because B here is 0 to
0 to P minus 1.
exact. So when they are congruent, because 0 to P minus 1 are different, I is equal to J, right?
Yeah.
Okay, so if you consider two different numbers here, because their i's and j's are different, then They are different mod p. So we see these, if you consider these numbers mod p, then one of them is 0, 1, 2 to p minus, right?
Yeah.
Okay, so we prove we have these two cases. Now, and the problem says our table is row valid, right? Okay, because it is row valid and we have only these two possible cases. What are the cases for
Well,
the
row
table?
values
We have two
also.
types of tables. They are what?
You have the tables with common difference 1 or sorry, not common difference 1.
Look, we said each
Um,
row contains 0, 1 to p minus 1 or p equal remainders. So if you
yeah.
consider the whole table, what are the possible cases?
So are there all mod p, all the like entries are the same, or they're all like one
Yes,
different?
if you consider first column, if first column is 0 to 1 to p minus 1 in some order, then for the next row, you cannot have p equal remainders, right? Because one of them
Yeah.
is here. So all rows
Yeah.
should be from this type, right?
Mm-hmm.
To p minus 1, or all of them without loss of generator. We can say 0, 0, 0, 0, makes 1, 1, 1, 1, 1, right?
Mm-hmm.
P minus 1, P minus 1. Okay, so we
Mm-hmm.
have these two types of tables. So try to, and they are row valid. So now prove that each of them is also column valid. Want another hint, or want to try the rest on your own?
I'll try rest.
Okay, sure.
So in the first case, if you have in the rows you have 0 to p minus 1, then in the columns you can always make it so that each column, because there's exactly p, there'll be p elements along the in each row, or there'll be p elements total that have 0 mod p, and you can make them all become
Yes,
one column.
you can move all zeros to the first column, all ones to the second column, all twos to this column, all p minus 1. And if you consider them, the common difference is what in each of them?
P.
P, exactly. In some order, for example, here we have p, 2p, 3p to p squared, right?
Yeah.
What about this case?
Then you have to make it into 0, 1, 2 to p minus 1.
Yes, because we have all zeros here, for the first column, you can move p. Because we have all ones here, you can move 1. For the next one, 2 to p minus 1. Then for the same
Yeah.
next column, we can say 2p plus 2p plus 1p plus 2 to 2p minus 1, right? And so on.
Yeah.
And in each column, common difference is what?
One column difference is 1.
Yes, good job. Okay. So we proved that for p it's possible, right? For primes. And we checked
Yeah.
n3. Now we should, now here, what should we do?
Should prove that composite's not possible.
Yes, or we can check n4, okay? So for n4, let's consider this table. The simplest table is what? That we can write.
Uh,
1. What's the simplest one? 1, 2, and
well,
what?
1, 2, 1, 2, 3, 4.
All numbers in order, right?
Yeah.
9, 10, 11, 12, 13,
Mm-hmm.
14, 15, 16. Try to prove that this table is not column valid, okay?
Mm-hmm.
Try.
Well, I don't know how to prove it for all general ones, but for the specific one, it's like there's no way to make one. There's no way to make one work.
Uh,
Actually, I don't know.
Look, for
Because like
example,
if you
yes, you said what?
well, for this particular example, you can't make. If you want to make one, the column in one has to be one like basically one. Well,
No, we can permute. We can permute
yeah, this
elements
one.
in each row, right?
Yeah.
Okay, so now we want to prove it is not column valid, okay? So if
But
it is column valid, so one can be, for example, suppose the column that contains one, then common difference can be what?
I think one common difference can be one. Well, it can be one in this case.
No, if common difference is one for the column of one. If
Yeah, so it
column
has. It can be four in this case.
mhm, or
Five.
5. Let's check. If it is 5, it is 11. This one 30. Are these two
Mhm.
possible?
I mean, the first one's possible.
What about the second one? The second one also is possible, right? Because they are not in the
Yeah.
same row. Also 1, 5, 9, 13. Both of them are possible, right?
Mm-hmm.
Okay, now let's check these two cases. So case 1 is this, case 2 is this. Now let's consider in the first case, the column that contains 2. So common difference can be what here?
Common difference can be four.
Can be only 4,
Like it
agree.
can be. Yeah.
Common
Okay.
difference cannot be 1 because 3 is here, cannot be 2. 4 is here, cannot be 3 because 5 is for this column. So it can be 4, it cannot be 5 because then 2, 5, 2 plus 5 is 7. If it is 5, it will be what? 2, 7, 12, 17. Not possible, right?
Mm-hmm.
It can only be 4. So 2, 6. Next one is what?
2, 6, 10, 14.
Is it possible? Yes, 2, 6, 10,
Yeah.
4. Let's consider something. In this example, we have 1, 5, 9, 13, right?
Mm-hmm.
It is column valid, this example, right?
Yeah, this one is.
So how can we make this to something that is not column valid? Let's do something. Here we have 1, 2, 3, 4, 5, 6, 7, 8. Let's change this example. So here, what numbers are left? 9, 10, 11, 12, 13, 2, 14, 15, 16, right?
Mm-hmm.
So do you agree? For example, here we can say 7, we have 7, 9, 11, 13, 15, and then say 12, 14, 16, 10, 10, 10, 12, 14, 16, right?
Mm-hmm.
Okay, so here if we check, again we should say 1, 5 and 1, 6, right?
Mm-hmm.
We have same thing for 1. 1, 5, 9, 13. 1, 5, 9, 13. Do you agree we can ignore first one? We can reject first one.
Yeah.
Okay, second case is left 1, 6, 11, 16. Now let's focus on 2. If we consider the column that contains 2, common difference can be what?
Common difference can be not 3. Can be 4. So
No, if you say 2, 6,
this.
then 6 is
Yeah, I can't. No, I know. So it can't be 3 either because
only
that
3,
would
right?
be
Because if
if
common
8
difference
isn't
is 1, is 2 is this, 3,
8's in the same one as 5 though.
4 is bad, right?
Yeah, but 8 is in the same row as 5, right?
Exactly. So this one we know is 2, 6, 10, 14. 4 is not possible. 5 will be 2, 7, 12, 17 is bad. For 2, 5 it's 8 and 11, but we know 5 and 10 are in the same column. So it is a counter example, right?
Mm-hmm.
Agreed?
Yeah.
Okay, so as you can see, we've written two of them, then we change these. So let's try next number that we should check is n what?
And we can check is n equals 6.
Exactly, because primes we proved it is possible. Now if we check n6, so 1, this one, this one. Again, if you use the previous one, you can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For example, 13, 14, 15, 16, 17, 18. And then what about these three columns? We should write what?
This is 19. Uh, well, it would be 19 to this, like 24. Do that.
Common difference is what? The common difference for this one
Well,
is 1. 1, 1. For
1.
this one is what?
1. 1.
We can write 1, 1, 1. But look here, we said common difference is 1, 1. But here 2, 2, right? So
Yeah.
here we want to use similar approach. 1, 1, 1. Then what about these three rows?
You could do 2.
If we say
19.
2, because look here we had two rows. We said odd numbers, even numbers. But we have three rows here. So it's good to
Oh, so you gotta do 3. Then 0, 1, 2 mod 3.
yes, exactly. 3, then you say, okay, 19 is here, 20 is here, 21 is here, 22, right? 25, 28, 31, 34. And then 23, 26, 29, 32, 35, and then 24, 27, 30, 33, 36, right? We want to
Mm-hmm.
prove it's a counterexample. And 6, again by similar approach. Try to reject this table, okay?
Mm-hmm. Okay, we're doing like the same thing. For 1 on the column with 1, your option is like 1, 7, 13 or 1, 8, 15.
Okay, so let me write. 1, 7, 13.
Mm-hmm.
Next one is what? 19 and 25, right?
Okay.
What
Yeah.
else?
Wait. Oh, yeah. And 1, 8, 15, 22,
3, 4,
29, 36,
1, 8, 15,
15, 22.
22, 29, right?
Yeah.
No, sorry. Oh, yes, 29, right? Next one is what? 1, 9?
Uh, you don't have to go. We have to go one more, right? You have 29, 36.
Oh, yes, sorry. Also for this one, we should write one more. 31 and 7, 36, so we cannot consider next one, right?
Yeah.
Okay, for the first one, 25 and 31 are in the same row, so it is bad. Right?
Mm-hmm.
What about the second case?
Second case, well, it has to be like 2, 7, 12, 17, 22.
We're gonna use 2, 7, then 12, 17, 22, 27,
Yeah.
or 2, 8, right?
Yeah.
But here we have 8. We cannot use that. 2, 9, 16, 23, 30, 37 is bad, right?
Mm-hmm.
For this case, what can we say here? 2, 7,
Well, it doesn't work because 22.
7, 12.
Wait, but yeah, also 22 is there twice, right?
20. We have also 22, yes. From two different ways, we rejected this. So N6 is not possible. Now we should try here to check NAB, okay? and A and B are greater than 1, we should try to generalize this. This is multiple of 2, 2 times a number greater than 1, here 2 times 3. Now we want to see for AB, how can we generalize this one? Do you want a hint for this part or want to try it on your own?
How to generalize it?
Yes. How to generalize this?
No, I don't know.
Okay, so here, I'm not sure how I generalized this before, but here, look, for example, when we had 2, we consider, for example, we divided by 2 and we consider last part, right? It was 2 times 3, we consider last 3 rows, right? So probably we should write numbers in order except last, for example, A rows, right? So let's check it. Here, we cancel it. We write numbers except, for example, last A rows. And this part is what? Is AB minus A, or A times B minus 1, right?
Yeah.
And we write numbers in order. So you say 1, 2, 3, 2, for example, AB, and then AB plus 1, all the way to 2AB. And second row and last row is A times B minus 1 times AB, right?
Yeah.
Okay. For these A rows, what numbers are left? We can write it in terms of N. Okay, for example, let's write in terms of A. So it's N plus 1, N 2N. It is A times B minus 1 times N, right? And this one is 2N, N plus 1, and so on. Now, what numbers are left? Here, you can say N squared. For AB minus this also, we can say it is N minus A, right?
Yeah.
So you can say N minus A times N. So you can say N squared minus AN, right? So here, as you can see, we wrote the numbers like this: 1, 2, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 18, then 19, 21. From here, we consider the numbers are in increasing order in each column, right? So you can consider from here N squared minus AN plus 1, N squared minus AN plus 2, right? And so on, and last cell is N squared, okay? Do you agree this is exactly similar to this one?
Yeah.
Okay, now we should try this. We should consider 1 and then consider 2. Probably we can reach contradiction, okay? So check if you can reach contradiction for this case.
I don't know how to make the generalization with the same like strategy.
Okay, so if we want to solve it like this case, we should consider 1 first, right? First of all, let's consider 1. So next element should be what for 1? Can be what number?
1 N plus 1.
Common difference is what?
Common difference can be N.
Yes. So it will be N plus 1, 2N plus 1, right? All the way to what?
All the way to the last A rows don't have the. Oh.
Last one is what? Look, 1, N plus 1. Nth element is what?
The nth element?
Yes, nth element. Look like here, 1, 7. 6th element is 31.
N squared minus N plus 1?
Yes, exactly, because we say n times n minus 1 plus 1, which is n squared minus n plus 1. So if you consider 1 and n plus 2, then it will be 2n plus 2, and nth element would be what in this case? Oh, sorry, here n, 2n plus 3. Nth element is what?
Nth element is n times m plus, or m plus 1 times n minus 1 plus 1. M plus 1 times n minus 1 plus 1.
If you simplify, it would be what?
N squared.
Exactly. Like this one, 36. Look, you should use this formula that an is a1 plus n minus 1d, okay? So nth element is a1 is 1. Common difference is what? N plus 1. Nth element, so n minus 1. So it will be n squared. Okay, so we have only these two possible cases, right? So for the first one here, we reach contradiction. How? We said 25 and 31 are in the same row, right? So here also we should prove this. So we guess that which two elements here are in the same row. We should prove.
Maybe n squared and.
You should prove two elements here are in the same row. Probably we should reject like here that is at
Yeah.
25, 31. Okay. On also 19. Here, 19, 25, 31. All of them are in the same row, right? So probably here you should prove that some elements here are in the same row. Want to prove this part on your own or
I don't
want
know
to
how to
eat?
prove that.
Okay.
I don't know how to prove that they're in the same.
N squared minus n plus 1. Do you agree this one is these elements are what? Elements that mod n are 1, right?
Yeah.
They are congruent to 1 mod n. Agreed?
Yeah.
So do you agree we have n squared minus an plus 1 here? Agreed.
Yeah.
And do you agree that here next element after this is what here in the same row?
N squared minus an plus. Plus.
Minus an plus what?
Well, I don't. What's special about the A rows? I'm so confused.
Look, it is exactly like this. Here a is what? In this case, a
3.
is what?
3.
Yes, here, a rows, a3, 3 rows here. We write the numbers in increasing order in rows, and then when we reach here, consider in the columns like this. So if you want to understand this better, it is exactly like this. So you should tell me next element after this is what? N squared minus an plus what?
Plus 1 plus A.
Exactly. Plus a plus 1. So do you agree from here, from this element? If two elements are equal mod A, they are in the same row, right? Agreed? Because
Yeah.
it is plus A. This one is
Yeah.
plus A, right?
Yeah.
This one is plus A. Here, mod A is 1. Here, mod A is 2. Here, mod A is 0, okay? Mod A is 2, 3 to A minus 1, and then 0, okay? Okay, so now if we consider this number and this number, both of them, do you agree, are congruent mod A?
Yeah.
So they are in the same row. And that's a contradiction. Okay, so we rejected this case. Exactly similar to this, right?
Yeah.
Okay, for this case, if we check this one, we understand that from 1 we cannot reach contradiction. So we have to check 2, and with 2 we can reach contradiction. Want to check next case on your own, or do you want a hint?
Hint.
Okay, so for 2, what are the cases? Common difference for 2 can be what?
M plus 1.
Yes.
And
And next one is what then?
2n plus 2.
Here, 2n plus 2, pay attention.
Or 2.
It's what?
N minus? You did n minus 1, so 2n.
2n. And here, look, we said 7 and 12 are in the same row. And if you check n plus 1, 2n are in the same row. So it is exactly similar to previous one, right?
Mm-hmm.
So one case is left. Want to prove it on your own, or do you want to?
But what do you mean case? Because isn't this general now? What is the 2, 9, 16? I'm very confused now.
What is 2, 9? Look here, I said, okay, one is, for example, in this column, when we permute rows. So 2 also should, there is a column that contains 2, right?
Mm-hmm.
For that column also, we should have an arithmetic sequence, right?
Mm-hmm.
So the common difference is 5, or is 6 is not possible, because then we have 2, 8. Or is 7. 7 is large, right?
Mm-hmm.
Or is 5. So we have only these two cases. So what's your question? Understand?
Just trying to apply it to a general one, I thought.
So in general, now here we have 2. Common difference is what? Can be n minus 1. It cannot be n, because 2n plus 2. So we generalize. So for 2, the other common difference is what?
n plus 1.
Yeah, so it will be n plus what? Next element, second element?
N plus 3.
Yes, next one is what?
2n plus 4.
Yes, and the last one is what?
3. Last one. All the way to 2 plus n plus 1 times n minus 1.
Yes, which is what?
N squared plus 1.
Yeah, so that's a contradiction, greater than n squared. So we rejected this exactly like this. Here we said 37. So that's how you generalize these 6 for AB, okay?
Mm-hmm.
Okay, so we proved if n is a composite number, it's not possible. If n is prime, it's possible. Understand?
Yeah.
Okay, what's the next question that you got stuck on?